title of my presentation is going to be a three-dimensional approach to atmospheric rivers from a tropical vorticity perspective. So I'm going to start with this situation in here. Before I'll tell you a very, very short story. When I was in undergrad, I had a professor that went into his classroom, into our classroom, and solved an entire problem set. He filled up 2 boards, and he said, in pure sheer excitement, I just finally solved this problem. It's amazing. Can you see the solution of it? And it's like, we all just said, yeah, it looks like a wonderful problem, but what is the question? I don't remember what's the question, but isn't it a wonderful solution? Reflecting upon science, I can see that sometimes we encounter that same situation. We collect data, which gives us our answers, and it's up to us to find out what is the question. So our motivation in this case, our answer was one of the missions of the CPEX campaign, in which this satellite image summarizes a little bit of what happened in there. The green box that you see in there, and that you will see in every box where you see, whenever I show a plot like this one of the satellite IR view, the green box would be the experimental domain, latitude and longitude of where the airborne field campaign happened, this particular mission. The red circled disturbance in there is the remnants of the specific tropical storm Beatrice, as it penetrated from the East Pacific coast of Gulf of Mexico, and the remnants, no longer a tropical status, went into the Gulf of Mexico, and where part of this generally disturbed the areas that covers most of the Gulf of Mexico. I put these arrows in here because it is also part, or it is interacting with this northeastward flux that we see in here, which, based on the structure that it has, it pretty much looks like something called an atmospheric river. But it is an atmospheric river. Is it really an atmospheric river in the tropics? That's the question that we will try to answer, among many. So CPEX was a 1-month field campaign in 2017 that occurred from May 24th to June the 24th. This field campaign, it was conducted with the NASA DCA, the plane that you see in here, that I'm marking here. Within the plane, there were several instruments were deployed, including drop zones that were going to be dropped from a certain altitude as we cruised into the disturbance area of the experimental box of the day. There were other instruments as well, including a second-generation precipitation K-band radar, and other instruments that we didn't use very much, that I didn't use for this presentation in here. So we will focus very much on the drop zone data and on the radar data. These are part of the photos that we saw during the campaign, and this is before taking off, sometimes that we couldn't take off because there's a big storm that wouldn't let us out. So back to the situation. We see this problem in here. Is there an atmospheric river? Well, our proposed approach, or our proposed answer, or our proposed question to this answer would be: the connection between tropical moisture and atmospheric rivers can be explained through moisture convergence, not moisture transport, induced by mid-level vorticity advection from the tropics into mid-latitudes. So since I'm going to talk about atmospheric rivers, and since I'm going to talk about the convection in the tropics, I will give you a brief background of both research fields that seem to be a little bit separate, but are connected in a certain way. So what about atmospheric rivers? The AMS glossary defines them as long, narrow, transient channels of strong horizontal transport of water vapor. They're commonly associated with low-level jet stream ahead of the cold front of an extratropical cyclone. Zhu and Newell drew where most of these structures, drew schematically based on water vapor flux, where most of these structures are found over the globe. And he claims or they claim that most of the water vapor in the atmosphere is transported through this mid-latitudes, which means off-tropical systems. So what are the main measuring variables for ARs? One of them is IWV and the other one is IVT. One of them is the amount of water vapor that there is, and the other one is where it's going. Water vapor content in a vertical column is IWV, which is basically precipitable water. It is vertically integrated, so it's a horizontal quantity. I call it AR substance. Now, where is that water vapor going? Is the water vapor flux in the vertical column, the IVT, and that is called AR transport. So these are the two main variables to measure if there's an atmospheric river and to measure its characteristics, right? What are the instruments and analysis products used to get these measurements? Well, there are several, but the most common ones would be satellite-based IWV observations using special sensor microwave imager, kind of like this photo on the left. And the other ones are reanalysis and model-derived analysis and dropsons, which we show in the right. The dropsons are of course, from airborne missions similar to CPEX, and we see them in here over this line. And the other product is an NCEP GFS, that's a model-based figure in here that we can see the IVT vector and the sea level pressure. Those are examples of how of instruments and products used to analyze these rivers. So what is the criterion to define if there's a river or not? Well, Ralph et al. Created, defined a certain criterion that has been modified over the years, but roughly it still conserves the same essence in 2004, which it has to be at least 2,000 kilometers long, as I'm pointing here, less than 1,000 kilometers wide. If it's too wide, it's no longer considered a river. And it has a threshold of minimum IWV, a minimum precipitable water, minimum water vapor content along the axis or throughout the feature. Any other thing that doesn't satisfy these three criteria, it is not considered an atmospheric river. So one of the most important questions of atmospheric rivers would be where is moisture sourced and where does it end? Where does it start and where does it end? So we have in here a schematic of the water vapor of an atmospheric river, and we have the tropical moisture in here, and we have something called the WCB. Well, the WCB, the warm conveyor belt, is supposedly the primary mechanism of vertical ascent from ARs into mid-latitude cyclones, and this is a mid-latitude cyclone. The tropical moisture export would be the source of the moisture and is defined as the polar transport of tropical water vapor from the tropics. So the main question is it actually transported directly from the tropics into atmospheric rivers? Well, that's still a question that is being asked nowadays. Here is a schematic, a cartoon schematic of Ralph et al. Of 2020 of how the WCB, the ARs, and the TMEs work. Is this really happening? Well, let's see. So the limitations in the current paradigm, as you can see in the past image, was can moisture source in the tropics be transported forward through ARs? Does evaporation occur at the entrance zone of an AR? Is large-scale precipitation concentrated near the exit? I have a typo in there. So we're going to see. Since atmospheric rivers are mainly, the measuring quantities are basically vertically integrated. They are horizontal. The vertical nature of it is masked in this analysis. Now, it is very useful as it is in mid-latitudes, but in the tropics, it encounters problems. So now that we have briefly described atmospheric rivers, let's talk about, how the tropics behave. The tropics can be, a good starting point for this is to talk about the weak temperature gradient approximation that works in the tropics, as opposed to the horizontal temperature, to stronger temperature gradients, which I call horizontal temperature gradients, and I call HTG. As you can see, this is a temperature climatology of how the tropics behave. This is for June. This climatology has gathered temperature data for the past 30 years, from 1981 to the year 2010. It is a little bit outdated, but it serves to illustrate that the temperatures in the tropics, all over the tropics, are pretty much uniform. They don't change very much. They're very hot, but they don't change very much. As opposed to outside of the tropics, mid-latitudes, where you see these isotherms, which are lines of equal temperature, are very close together, which means that the gradients are stronger than they are here in the tropics. So that creates a distinction between how moisture is transported and moisture convergence happens in both of these areas. So what about the weak temperature gradient approximation? A few features that can be considered through years and years of research. People have found, several authors have found, that there are small buoyancy anomalies. There is absence of adiabatic processes leading to strong updraft, so its vertical velocity is kind of not as strong in the tropics, not expected to be as strong in the tropics as it is elsewhere. All heating is translated into vertical motion, and the average vertical motion is accomplished by either radiative cooling and convection. I highlighted it because I'm going to talk basically about what convection is. So speaking about convection, there are three thermodynamic constraints that govern the average behavior of convection in the tropics. There is moisture quasi-equilibrium, which I will refer to as MQE in the rest of this presentation. There is the effect of saturation fraction in precipitation, which is very much related to MQE. And there is boundary layer quasi-equilibrium. Now, I highlighted only the first two ones because the last one, even though it is important for convection, it is more important in studies of tropical cyclogenesis, where there is a low-level vortex that will eventually become, well, there's a low-level vortex or a mid-level vortex, and it is important for the generation of tropical cyclones. Even though one of my case studies involves a tropical cyclone, the focus of my work in here doesn't include tropical cyclogenesis. So, everyone who reads a book on atmospheric thermodynamics runs the risk of getting overwhelmed by a seemingly endless list of precipitations. This is in the book of A.P. Siebesma, and I actually thought it was really funny, and it's very true. But in cloud physics, he says, one essentially needs only three temperatures. One for dry adiabatic processes, which is potential temperature. One for moist adiabatic processes, equivalent potential temperature. There are other ones, but there's basically this one. And one for measuring buoyancy, which is vertical temperature. So speaking about equivalent potential temperature, one great use for it is to measure a conserved variable. When I say conserved, it's conserved under phase transitions. It is conserved both if there's a transition from water vapor to liquid water or to ice. So this is very useful for our research. What else can we say about moist entropy? Well, it is under constant temperature. It is a measure of the moisture content. What if we have a saturated? What if the moist process that we have is saturated? Then we can say that it's also conserved under phase transitions because it's also a type of moist entropy. But the difference would be in here that at a given pressure level, it is a measure of temperature. So these two quantities would be very useful for us to associate moisture and temperature. Another great use for it is to see a vertical sounding. This is an idealized vertical sounding of a perfectly adiabatic process where any partial ascent is undilute. It is not disturbed by absolutely anything, and there is no turbulence. There is the ideal in here. But let's consider this idealized model. In this one, the blue line is the moist entropy, the red line is the saturated moist entropy, and the dotted line is where the particle ascends. It can actually ascend from the surface with a value of moist entropy that is exactly the initial value of the ground, but it can also be with an average from 0 to 1 kilometers, and it will go up. As it goes up, the moist entropy and the saturated moist entropy values are equal. So this is the point where it saturates. And as it saturates, it reaches the level of free convection, where it will keep ascending because the buoyancy of the air particle becomes larger than that of the environment. It will keep ascending up until its buoyancy runs out, which is the level of neutral buoyancy, which is where buoyancy of the particle is smaller than that of the environment, thus it can no longer ascend freely. So this is the idealized model. What is the problem with that? Clouds are subject to turbulent mixing with the environment. And this turbulent mixing, we will call it entrainment. So in the idealized model, entrainment only happens in the subcloud layer before it becomes before it starts ascending and becoming a cloud. And detrainment only happens at the very top. But in the non-idealized way, it happens in the tropics, and you see that ascent is, where I have said that vertical ascent is not exactly the perfect adiabatic. Lateral entrainment and detrainment are very important processes. And there are very important processes in something that we call near zero buoyancy. And this is very important for the processes in the tropics. And that pretty much indicates that entrainment and detrainment are variables that should be considered in the tropics. This picture in here shows very much of what we're talking about. I am not entirely certain where this happens in here, but this is a good example of a photo taken of shallow convection during a CPEC mission, where there is a convective scale subsidence, and probably this cloud is affected by entrainment, by lateral entrainment and detrainment. So let's talk about saturation fraction and instability index, now that we have talked about moist entropy, saturated moist entropy, and entrainment. So saturation fraction is basically the ratio between precipitable water and saturated precipitable water. Another way to call precipitable water is the integrated water vapor that the atmospheric river community uses. But why do we divide it over the saturated precipitable water? And I highlighted it in red because precipitable water it talks about the moisture, and saturated precipitable water it's a function of temperature. So we make saturation fraction both a function of moisture and temperature. This would be related to something else that we call instability index. Instability index is the difference between the saturated moist entropies at low levels and at mid levels. So saturated moist entropy at a defined pressure level is the difference, it is a measure of the temperature at these two levels, where, well, then the instability index is a function of temperature, so it is connected in a certain way with saturation fraction. Why is it useful? Because instability index can tell us the nature of vertical temperature anomalies in a specific column. So if the instability index is low, near zero, it means that we have cold over warm anomalies, temperature anomalies. So, and if we have high instability index, we have the opposite. Sorry, I said it the other way. If we have low instability index, we have warm over cold anomalies. It is cold at the bottom, warm on top. If we have high instability index, it is the opposite, and it is warm below and cold above. All right. This is an example plot of how saturation fraction and instability index looks like. As you can see, it seems that when one of them goes up, the other one goes down. So it seems that there is an anti-correlation between both of them. And this anti-correlation, we call it is the basis of the concept called moisture quasi-equilibrium, which we had talked about, MQE. So MQE is a convective feedback mechanism defined by the anti-correlation between saturation fraction and instability index, as you can see in this image. So we'll talk a little bit about what moisture quasi-equilibrium is with this very nice diagram that appears in the newest Raymond et al. Paper. So there are three basic states of moisture quasi-equilibrium, which it says when the environment is too dry, when it is just right, and when it is too moist. So consider that we have a given level, a given value of instability index, but the environment is too dry. Convection by parcels, because of that instability index, will ascend in that hostile environment. Entrainment goes into the picture now. There is entrainment in here, but it will entrain dry air, which will eventually make the cloud, the parcels in the cloud, to fail. But as the clouds fail, well, they detrain, and they detrain moisture air, which moistens the environment. As the environment is moistened at any level, at the level that it reaches, it creates a warmer temperature anomaly because moisture processes are warmer. So it starts modifying the instability index. In a subsequent process of convective ascent with a lower instability index, but still a subsequent process, it will detrain, it will ascend, and the entrainment will be more moist up until there is a net tendency to get into a Goldilocks point, which would be just the right point. So as the instability index is sacrificed to go into lower values, saturation fraction reaches an optimal value where it can actually be kept in equilibrium. And this is the optimal moisture, the optimal saturation fraction. So you see, it depends on both of them, and entrainment is a very important part of this. If there is too much moisture at the beginning and a large instability index, well, convection will be vigorous, and there will be a top-heavy convection like this one in here, like a sad sign in here, and well, it will rain. The rainfall would be significant, and after rainfall, because of rainfall, the column would dry. So that creates drying of the column, and that's not the optimal value. So this is just right in here, which is deep convection. So now, we see that there is a certain equilibrium between the local environmental properties that relates moisture and temperature and the optimal amount of it. Is there a dynamical variable that can affect this moisture quasi-equilibrium process? Well, there is. And this variable is the absolute vorticity. Strictly speaking, is the potential vorticity, but potential vorticity affects temperature structure modifying vertical temperature anomalies. But due to the weak temperature gradient approximation in the tropics, the dominant component of potential vorticity is the C component of absolute vorticity. So this is what we care the most. So this is schematically what is shown, what happens. If there is a PV anomaly at surface, it creates a warm temperature anomaly at low levels. But if there is a PV anomaly or an absolute vorticity, a C component absolute vorticity anomaly at mid levels, it creates warm over cool anomalies, which is what I told you is related to a very low instability index. So vorticity affects the instability, it affects the temperature, dipole structure, which affects the instability index, which affects the saturation fraction. So our main question is, if the vorticity is advected or moved somewhere by another process, can it actually create moisture convergence somewhere else? Well, we'll see when we see the large scale conditions. So, well, let's see before we see the first case study, see the data that we had basically dropsondes used for all missions in two cases, in the two case studies. We had the APR2, the airborne precipitation second generation radar, which we used for only one mission, mission 5 was the first case study. How does a typical dropsonde measurement look like? Well, here it is how it looks like. Sondes are dropped from a certain altitude up until they reach the ground, and while they are in their trajectory from the level of launching to the ground, they are collecting data. These are the horizontal components of the wind, and these are the temperature and the dew point, which is related to the relative humidity, and that's it. These are vertical profiles. It's a variable versus a pressure level, which would be a two-dimensional thing. Now, we want it to be, we want to have a three-dimensional product. We want to see what happens in between where the drop zones are dropped. So we had something called 3D VAR. This is a method to analyze the drop zone sets. But this is locally within the experimental grid of each mission. To see the large-scale conditions, we use the NCEP FNL model analysis. So what is 3D VAR? 3D VAR is a three-dimensional variational method used to visualize dynamic and thermodynamic structure within the bounds of the experimental domain for each mission. So it goes from here, where we have the experimental grid. This at the top is where we dropped all the suns. These are the locations where we dropped the suns. And this small cube in here, which I created online, basically illustrates how it blends everything together from the locations of the suns, the profile it creates, and then we created an interpolated grid with this variational method up until we have an interpolation volume from which we can have vertical cuts or horizontal cuts and we can see what happens roughly in between where the drop zones are dropped. So we can see what happens inside here, even though we only dropped in these particular points. So case study 1, a Gulf of Mexico atmospheric river. It was comprised of 2 missions, and the experimental grids of which is indicated here. This is the situation for June the 2nd of 2017, which corresponds to mission 5. Mission 4 corresponds to June the 1st, 2017, which is close enough to say that this specific, this satellite image applies to both of them, even though it's not exactly the same. So we will analyze 3D VAR with, we will have 3D VAR data analysis with both of them. So at first, since I had talked about a northeastward direction of the general flow according to the satellite image, I rotated the coordinate system for this particular case study. Instead of the conventional YX, I rotated it 45 degrees, and we have a cross system and a long system. So that can tell us what moves along the flow, which would be expected, anything that moves along the flow would be expected of atmospheric rivers, and cross flow would be not part of it and against it, especially at low levels. So how does the wind look? Well, basically in here, we can see 2 different situations. The situation before we had this particular view in here is that of mission 4. What we see in here is basically horizontal shear in here, which indicates that vorticity structure is being developed. As opposed to what happens in here, yes, there is also horizontal shear in here because it's negative and this is positive, negative, positive, negative, positive. But also besides the horizontal shear, there is vertical shear in here. There is an eastward tilt of this structure. There is also a low-level jet, which we see in the across wind, and this low-level jet is across it. We expect that if it were in the conventional sense of an atmospheric river, we expect the low-level jet to be along, but this is across. So it keeps us wondering. How does the vorticity look like? As I said, there was in mission 4, there was a developing vorticity structure, and it seems very enhanced, but it pains down and it actually stabilizes it a little bit more into a mid-level structure in here with a very eastward tilt, and we wonder, why does it have that eastward tilt? Well, let's compare it up. Let's see first how the temperature structure looks like. Oh boy, warm over cold anomalies, very much with an eastward tilt in mission 5. There are also warm over cold anomalies in here, but it's related to the development of the vorticity structure. But in here, there's also this other structure, which I will talk about later, and this is also this is called a cold pool. So comparing the absolute vorticity and temperature anomalies, we can see here that what creates the eastward tilt in both of these structures, or basically the vorticity structure that influences the temperature structure in the end, the temperature anomaly structure, would be the vertical shear that we have in here. So we locally see vertical shear, vertical wind shear, both in the vorticity structure and it's affecting also the temperature structure. How does the saturation fraction instability index picture look like? Well, we see in here the saturation fraction is pretty much has a tendency of going down as it advances in longitude. And as it goes down, the instability index goes very much up. This is related to something called top-heavy convection. As I told you before, if it's too unstable, it creates vigorous convection, and the convection is top-heavy. Whereas in mission 5, we have the opposite, which would be bottom-heavy convection. We have a Goldilocks point in here in 92, let me see if I can see it, in 92 west, where saturation fraction would be optimal and instability index would be minimal. But the minimum instability index, we can see that is very negative as well, and that is related to what we see as a cold pool. Now, how does the vertical mass flux look like? As predicted, it looks like this. In mission 4, where the vorticity is developed and the stability index is growing, well, it is top-heavy convection, right? There's convergence very much, not much at lower levels. It is much at higher levels, and it paints out in here, and it is divergent elsewhere. Whereas in mission 5, we have bottom-heavy convection, which looks like this. Now, about the cold pools, we see the moist entropy contours, how they look like for mission 5. And I circle the regions of what you see as cold pools because this is, in terms of moist entropy, there is a dip at the surface. You can see it in here. And there's also in the same place a dip in saturated moist entropy at the surface, which indicates that at this region, moisture and temperature are lower. There is an anomaly both in moisture and in temperature. We can also see it in relative humidity if you don't want to use moist entropy and saturated moist entropy, but it is evident, but not as evident as with saturated and moist entropy and moist entropy. Now, how does it look like in terms of saturation fraction and stability index? Well, this cold pool happens in between 93 and 92 west, and you can see that between 92 and 91 west is where we have the optimal value right next to the cold pool of very close to the cold pool of saturation fraction and the minimum value of instability index. Now, it seems that it is that there was a previously dominant convective regime in there, and it is being rained out. So another tool to see it is finally we see the radar plots. These are KU band radar plots, and it measures reflectivity. So just to give you a glimpse of what it is, ice is more reflective than water. So we have a freezing level in here at 4 kilometers, and this horizontal level, this horizontal band that we see in here that is actually dissipating, not very clear, is called the bright band, which is where snow is located, and it's actually melting. Now it's melting very much more in here, so it looks like it is actually being rained out around 92, where the cold pool is at. I drew vertical lines in here to see where I have, at instance at 96 west, we have convective towers going up, both at 96 west and around 93 west. So it is also indicated. So this that we see as increases in moist entropy, we'll also see it indicated here in the radar plots. So now that we have seen the local characteristics, we now can see the large scale characteristics with the NCEP FNL model analysis. So what is FNL? FNL is a spectral analysis system that sees from previous NCEP GFS model results, but it couples it with observations to yield the final initialized output for the next GFS run. This weighting process allows the inclusion of unconventional data in the analysis. And by unconventional data, one example that it's shown in the past, in past analysis, is the MJO. But in our case, we expect the unconventional data to be what I'm looking for if the vorticity structure being advected into mid-levels and affecting the atmospheric river, right? So it allows the inclusion of unconventional data in the analysis in absence of local approximations. So how does it look like? I did cross-sectional, okay, this is the image of horizontal cross-sections, just in terms of, in a specific latitude, I averaged with respect to the latitude, and I did longitudinal cross-sections of how the along and across wind looks like. From the across wind, I can tell you in summarized terms that all of them, this is 21 west, 25 west, 27, 29 is already, in mid-latitudes, or already in the Western Atlantic. This is in the Gulf of Mexico, the first three. In the first three, we see that there is significant low-level across flow. There is low-level cross flow, both 21, 25, and 27, which would be against, or which would be contradictory with respect to the definition of atmospheric rivers. It's not actually connected to the flow. It's not transporting directly moisture into the atmospheric river. Now, how does the along flow look like? Well, there is not much shear at 21 west, but there is a lot of shear. It is visible, it's evident at 24, at 25, at 27. And when we go to the Western Atlantic, there is not much cross flow in there anymore. So there is not much cross flow, and there is not vertical shear anymore. So there is a shear structure in here. So how does it look in the plan view? I made an animation of how it happens from start to end, but so you don't have to actually follow it to see, because it is quite hard, especially because I haven't said what each variable is, and I'm going to say it right now. The filled contours indicate mid-level vorticity, the average for the levels in between 500 to 700 hectopascals. Okay, so green is enhanced vorticity, red would be low vorticity. The wind barbs are basically with the average direction of the wind. If you wonder, with a decimation factor of 4, which means that it skips every 4 vectors, so it doesn't saturate the plot and it doesn't look ugly. And the scaling factor, both horizontally and vertically, is 0.2. So this indicates the mid-level flow. It's also averaging between 500 and 700 hectopascals. The blue, the solid blue contours that we see in here are high saturation fraction, which means 0.7 and above values. And the dotted or the dashed green, bright green contours are low instability index. And with low instability index, I mean from -5 to 5. So it seems like it is intentional for me to be looking for the places where the moisture quasi-equilibrium is just right. So we can find the optimal saturation fraction, which happens when the instability index is very low. Okay, so we see where this simultaneously the regions in the Atlantic, in the Gulf of Mexico, Caribbean, and Western Atlantic regions, the regions where it happens, and this is how it starts. This structure that I have circled in magenta is the landfall of Tropical Storm Beatrice. So you can see that it has an enhanced vortex even though it's making landfall. And it also, it has regions of high saturation fraction and low instability index to be expected from a tropical cyclone. Now, how does mid-levels, how does it look in mid-levels, both for mission 4, which is June the 1st, and mission 5? Well, in mission 4, we see still the vorticity structure of Tropical Storm Beatrice, but we see other vorticity structures in here that are not are not related. So I can't say that exactly the extratropical cyclone transition became the vorticity. It influences the vorticity that eventually fed into the atmospheric river, but there's also other processes going on, like this process in here. And we saw it in here in the very corner of mission 4 as an enhanced vorticity structure that is forming in mission 4. Now in mission 5 is the most interesting thing. This yellow box in here indicates, well, the yellow box for all means the experimental domain for mission 4 and the experimental domain for mission 5. So for mission 5, we have a very interesting situation. We have enhanced patches of mid-level vorticity. I'm talking about the C component of absolute vorticity. And we have this large region of high saturation fraction and low instability index. So how do I support the theory that vorticity is actually vorticity advection by the shear that we see in here is being advected into mid-latitudes? Well, vorticity is being advected, probably not, it looks here that not continuously, but the continuity is being given by both the saturation, high saturation fraction and low instability indexes. That is the point of influence, okay? So that is how it happens. Now in low levels, how does it look like? Well, at low levels, we can see that there is very much a cross flow. There is cross flow coming from the Caribbean. There is cross flow in here. It tries to tilt a little bit into the atmospheric river, but it is not very strong to support the notion that what's happening in here without the vorticity, it is a pure tropical moisture export. So based on this, without looking at saturation fraction and instability index, well, there would not be a net, a direct transport from through a low-level jet in here in this region into mid-latitudes because there is significant cross-flow. But the cross-flow is related to the vorticity structure that as we saw previously. In the vorticity structure, as it is advected by the vertical shear. We don't know where that vertical shear comes from, but we do imagine that it comes from the influence with the interaction with the atmospheric river. The vorticity, as it is advected, it affects the instability. It affects the temperature structure, the vertical temperature structure, which affects the instability index, which affects the saturation fraction, which eventually feeds into the atmospheric river. So that was case study 1. Case study 2 is not as pretty as it looks like. That one was a yes case, and this one would be like not very much. So briefly, what we have in here is we followed the genesis, development, and decay of Tropical Storm Cindy. Tropical Storm Cindy formed in the Gulf of Honduras, and this corresponds to mission 16. Missions 19 to 21 are Cindy as it moved into the Gulf of Mexico. The satellite image that we have in here corresponds to June 21st, which is the green, the bright green experimental box that we see in here. And as we see in here, this is the circulation center of Cindy. And this long thing is actually the flux, the moisture flux of Cindy. As we can see, the circulation center of Cindy is very much clear. We want to know kind of why, and we will explain. I will explain why this happened. The other two missions are the mission. This is mission 13, and this is mission 12. We don't have mission 11, sadly. So the part of the genesis and the development is not as interesting for the purpose of this research as what happens when it decays, which is I will focus on. So in here, I start instead with the large-scale view, the FNL views. So we compared the low-level vorticity, MQE, and low-level wind vectors, as we did for the case study 1. This in the top is for mission 13, June 2017. And this is the mid-level vorticity for the same day, okay, the day before the clear circulation center of Cindy. So we see here that the low level and the mid-level vorticity structures, they are a bit tilted. They are not very much vertically aligned with each other. But we also see another situation that we have saturation fraction and instability index are not quite synchronized with each other. There's also there seems to be a trough, a low pressure system affecting it over the continental United States. But I can see in here, interpreting it as this elongated portion of high saturation fraction. This doesn't, in terms of an atmospheric river, it's not more than 1,000 kilometers long. It's not more than 2,000 kilometers long. It's not even 1,000 kilometers long. So this wouldn't be an atmospheric river on its own. But in terms of the definition, there would be horizontal transport of moisture, which we expect most of the moisture to be at low levels, and we expect it to be directly in here with high moisture. So now the flux, the low-level flux, is very enhanced from the Caribbean directly into the center of circulation of Cindy in the Gulf of Mexico, but the instability index is not very high. There's a similar situation in here in terms of the mid-level flux. So there is both the low level and the mid levels of flux are aligned, and they transport moisture into the center of circulation. But what happens in here, because we are transporting, moisture is being fed into Cindy, but what we saw the following day is that the eye is clear. So let's compare how it looks like, how the low-level vorticity, winds, and MQE looks like for mission 13 and mission 14. Well, in mission 14, this tropical moisture export that was present in mission 13, well, it pretty much disappears. There is flow in here, but now the instability, the low instability index contours, the high saturation fraction contours, and the are more aligned with the circulation center, with the vorticity structure of Cindy. So what happened? Let's see what we locally caught. So this is how the vertical velocity looked like for all four missions while it was during the genesis, while it was developing high vertical velocity. Now, when it was developed, we can see that here is the very much robust. It is indicative of a very much robust vorticity structure of Cindy. But in the following day, there is a very enhanced region of subsidence, of negative vertical velocity. So there is a lot of subsidence next to the center of circulation of Cindy, and it was related to what happened the previous day. Now, let's see how the vertical mass flux looks like. Well, that also affects. For mission 10, it starts being bottom heavy, which is conducive for tropical development. Then mission 12, it becomes incredibly top heavy. Mission 13, it is less top heavy, but still top heavy. And in mission 14, averaging the vertical mass flux for all the region, including the subsidence and the center of circulation, we see that it is mildly bottom heavy, but this is deceiving. Let's see just what happened in mission 14, considering different ranges. Now, if we consider the range of 94 to 89 west longitude, which is only where the center of circulation of Cindy was, it is quite bottom heavy. If we consider the whole range, it is very divergent. But if we consider only the region east of Tropical Storm Cindy, where there was a region of subsidence, it is incredibly divergent. So how does moisture quasi-equilibrium look like? Well, for all these missions, it seems that there was a net tendency towards this Goldilocks point, that it was pretty much being reduced. This is the these are scatter plots of saturation fraction versus instability index, and this is the how much correlated they are. So just 0.76, then it increases to 0.98, and you're perfect. But it starts decreasing in here, and at this point, I don't even draw the trend line because they are not connected. And there's the main problem in here, in this region, where both saturation fraction is increasing at the same time as instability index. So instead of anti-correlation between both, there is a correlation between both. And I call that a supercritical moisture quasi-equilibrium. So it actually is being like going against quasi-equilibrium. Supercritical quasi-equilibrium conditions can be sustained, but not, if it's a trend, it can no longer be sustained. And this happens in the region where the tropical moisture export it's supposedly happened in the next day where the subsidence region is at. So was it a tropical moisture export? It pretty much isn't. So what do I conclude from both of my cases? After dynamic and thermodynamic features are analyzed, observational evidence of MQE is found both locally in dropsum-based 3D VAR analysis and in large-scale FNL model analysis in a narrow poleward channel extending from the Gulf of Mexico into the Western Atlantic. The atmospheric river in the Western Atlantic extending into the Gulf of Mexico is characterized by strong poleward motions and mid-level vorticity advection driven by the vertical wind shear. Cross-flow into the jet in tropical regions rules out the possibility of a pure tropical moisture export. So a conceptual approach, the conceptual approach of this dissertation to analyze the tropical connection with atmospheric rivers is proposed, combining the existing link between vorticity and moisture quasi-equilibrium. This approach addresses the conceptual limitations brought by the conventional definition of atmospheric rivers, which masks vertical motions. It shows the key role played by vorticity advection at mid-levels by the action of vertical shear, in which mid-level vorticity induces moisture convergence as it is deformed and displaced poleward. And finally, observations of a tropical moisture export in the Western Caribbean indicate these fluxes interact destructively with a nearby tropical cyclone. This is evident both in observed evolution of tropical cyclones and the observed loss of moisture quasi-equilibrium. We could maybe say that there was a loss of balance, but I'm not sure of that, of the balance flow. At least we can say that there was a loss of moisture quasi-equilibrium, and that was related to how the center of circulation got cleared the next day on mission 14. So before I go into the thank you, to the questions part, before you can ask me questions, this is a long journey, so there's a lot of people to thank. And this, this is where it gets into the web works. I want to thank a lot of people. But first, I want to thank my mother. I wouldn't have done this 15-year journey without you, although 7.5 years in Costa Rica and the 7.5 years here in the US. Plus a pandemic, I haven't seen you all year. I yearn to see you, but I know that it is more important for you to be safe, for us to be safe, that this pandemic one soon will be over. I want to thank the Claros family, my family, and I want to be called, in case I survive the butchering of my committee, I want to be called Dr. Claros. I want to thank them for their support throughout all these years. As it says in The Godfather, you can never lose your family. I want to thank my best friend, Crystal. You've been my friend for the past 6 years. I didn't know you before then, but you've been my tower of 42 in these years. Many of these years have been really hard, including this one and in 2015. And I cannot repay all you have done for me. You have been the best friend that I've ever had. I want to thank Paige Hansen, who doesn't like photos and is now in Washington and is also not able to see it because she's working. I want to thank Priscilla Elizondo, friend from all the way to Costa Rica. We met in Costa Rica. She went to Utah to get a PhD in math. I want to thank her very much. I don't know if she's part of the conversation, but I still want to thank her. Lorraine, my old office mate, thank you very much. I miss you very much. I no longer have that office anymore, so it's no longer our office. I want to thank Shani, one of my best friends from the GSA, and now a postdoc at UCSD. Maybe we'll meet together soon and maybe there. I want to thank Ellie House, who's also working, Amy Tattersall, who has a class right now, Vicki Kelsey, who is tuning in here. Thank you very much for all you've done before you left. The grad students, most of them who are gone, and I'm not here because I didn't have time to invite them. Phil Segan. Phil, I have to thank you very much because you told me to buy a 1576 mainframe computer, the 50-pounder that I have at home. That was my master's degree, and that's my PhD. I want to thank Sancology for letting me use all your library. When we shared an office, you had a vast library. You saved me from buying many books that I couldn't afford back then, and you just had them at reach. Thank you very much for that help. Ryan and Lacey Lapham for all the gatherings, all the kickbacks. Perry Ann Johnson for all you helped me in that very hard inverse methods course. We worked together as a team. We had a perfect synergy in that course, which was the hardest of all my grad school, and I can't thank you enough. I want to thank my mentors, Dr. David Raymond and Jill Caput. David Raymond, who knows me from the very start, even from Costa Rica. We met when we were in crutches. When I was in crutches, I actually took a taxi to meet him, and it was one of the best decisions that I could ever make.
Jose, can I bring you in here? Could you be? Yes. We're kind of short of time, so I think simply showing people on the screen is fine for the all right. For the mentors. Okay. So I want to thank all these people. I want to thank the people, my research team at Tech. I want to thank my peers at CPEX, which are not shown here. My peers at Utrecht, which I show in here. Justin, thank you very much. In the discussions that I had with all the professors in Utrecht, George Kilatis, and the others. My friends in Costa Rica, Rafael Oriamuno, and I want to thank and the others. I want to thank my Twitter peeps, several of them who are tuning in right now. The GSA, Karen, Barbara, Deneen, Lexi, Teresa Hollis, Dr. Peter Fea, and Michael Vogel. And this is pretty much, these are my inspirations, and thank you very much. I'm open to your questions. Okay, so we have time for a few questions. Maybe you could put me on as co-host again, Jose. Yeah, hold on. Yes, you are co-host again. Okay, so raise your hand on if you have questions. And so I see one from, wait a minute. So I don't see anybody raising a hand. Oh, Carlos. Carlos.
Hi, Jose. Can you hear me?
Yes. Yes, I can hear you.
Okay, good. Good. Well, thank you for your presentation. It was very, very good. I really enjoyed it. So, but I have a simple question. To all this time, it's not clear to me what is the life cycle of an atmospheric river and what is the time scale for that. So, what is the time scale of the atmospheric river that you talk about today?
Well,
do you have a sense for that? I know that you only have some soundings and a snapshot, but as you mentioned the FNL, perhaps you got a better idea what is the time scale that we're looking at here.
It can be several days, and the atmospheric river community has an answer for that in TW3E. And they describe it in terms of categories from category 1 to 5, as with hurricanes. It can be from 1 day to several days to even weeks. This one, I believe that it lasted 3 days, but I didn't officially count it as such because I didn't do an AR analysis per se. I would probably like to do something like that if I work with them at TW3E. I don't even know if they actually recognized it or not. They're mostly they mostly think of these ones over the Western Atlantic if they affect Europe, and I think this one didn't affect Europe.
Okay, thank you.
You're
Okay,
welcome.
any other questions at this point? Actually, if you have a question, just unmute yourself and announce yourself. That's easier.
Yeah.
Hi, this is Susanna. Hi, Jose. You did a fantastic job. This is super outside of my field. So I just kind of wanted to understand, where would you most like to see this research applied in the future? What could you see this going towards 5-10 years down the line?
Well, that's an excellent question. And so I very much want to address the limitation of this the atmospheric river paradigm. And to actually do that, I pretty much need to know what other great authors did in the past, like Zhu and Newell, who created several years of climatology. I have, as you see, one case study for ARs in the Gulf of Mexico and one case study for a potential TME in the Western Caribbean. So I would like to very much expand that into several other cases. And that means not only observations, that means modeling. So if the models are not seeing it, I mean, if only FNL is seeing it, FNL sees it because of the data. But it is important for also GFS to see it. It is important for ECMWF to see it. And it is important for WARC to see it. I want to test my theory through all these ways, through models, through observations, in the more difficult cases of atmospheric rivers, where there is a visible tropical connection, but it is not known. So that also includes the other atmospheric rivers in other regions of the world, not just the Gulf of Mexico. And I would also like to integrate this thing with, as you see, I had one example of a cold pool. A cold pool is very localized and pretty sneaky. I would like to have more data sets in which I can actually try to associate these cold pools with other situations and see if they have a relation with the atmospheric rivers. So I do believe that this research is very promising, and I really want to continue doing it for the future. Just to give you a few examples, this year, this hurricane season gave me a lot to think about, and let's just go into the example of the forest fires in California. What happened before? The Weather Service in the Bay Area considered that Tropical Storm Fausto, which was in the East Pacific, in the Northeast Pacific, close to Baja California, that there was an atmospheric river that was feeding moisture. They said feeding moisture into Tropical Storm Fausto, but in a conventional way of feeding moisture being fed from the tropics, I mean, precipitation would be quite a stratiform, and that one was pretty convective. It was very much characterized by dry lightning over all California, Oregon, and even Washington, which propagated fires in there. So I want to see. I hadn't had time to do that. What really happened there?
Okay, Jose. Okay, I think we need to bring the public session to an end as in the interest of time here. So let's everybody thank Jose. You can unmute yourself and give him cat calls or whatever you like, and we will then proceed.
Yay, good job,
Jose.
Okay, well, all right. So thank you very much.